Most people see a battery bank and think of it as one large battery. But that battery bank is actually made up of smaller parts. Those parts may be individual cells, complete batteries, cables, protection devices, and equipment that controls how the stored energy is used. This week, we are going back to the beginning. Before we start talking about BMS wiring, battery cables, fuses, busbars, or connecting a battery to an inverter, we need to understand what we are actually building. By the end of this video, you should have a basic understanding of the difference between a cell, a battery bank, and a complete energy storage system. You should also understand why voltage and amp hours both matter when comparing batteries. Let's start with the smallest part. A cell is the basic building block of a battery. A common LiFePO4 cell has a nominal voltage of about 3.2 volts. The word nominal simply means the voltage used to describe the cell. The actual voltage will move up and down depending on whether the cell is being charged, sitting at rest, or supplying power to a load. A cell also has an amp-hour rating. For example, a cell may be rated at 3.2 volts and 100 amp-hours. To find the amount of energy stored in that cell, we multiply the voltage by the amp-hours. 3.2 volts multiplied by 100 amp-hours equals 320 watt-hours. That means the single cell stores about 320 watt-hours of energy. Now let's take 4 of those cells and connect them in series. When cells are connected in series, the voltage adds together. 3.2 volts times 4 cells gives us 12.8 volts. That is how a common 12-volt LiFePO4 battery is built. We normally call it a 12-volt battery, but its nominal voltage is actually 12.8 volts. The same idea applies to larger battery voltages. 4 cells in series make a 12.8-volt battery. 8 cells in series make a 25.6-volt battery. 16 cells in series make a 51.2-volt battery. These are commonly called 12-volt, 24-volt, and 48-volt batteries. So, when you hear someone talk about a 48-volt LiFePO4 battery, they are usually talking about 16 3.2-volt cells connected in series. Now we need to separate the words battery and battery bank. A battery is a group of cells connected together. A battery bank is one or more batteries connected together to supply the voltage and storage capacity needed by the system. One battery can be considered a small battery bank. Several batteries connected together can also make a battery bank. The important part is that the bank has to match the equipment it is being used with. A 12-volt inverter needs a 12-volt battery bank. A 24-volt inverter needs a 24-volt battery bank. A 48-volt inverter needs a 48-volt battery bank. This is not something we can guess at. You cannot connect a single 12-volt battery to a 48-volt inverter and expect the system to operate correctly. The voltage of the battery bank and the input voltage of the inverter must match. Now let's look at the difference between a battery bank and a complete energy storage system. The battery bank stores the energy. A complete energy storage system includes the parts needed to control, protect, and deliver that energy. Depending on the system, that may include a BMS, fuse, breaker, disconnect, battery cables, bus bars, inverter, charger, monitoring equipment, and a battery enclosure. The battery may be the largest and most expensive part of the system, but it is still only one part. This is an important point for new DIY builders. Buying enough batteries does not automatically give you a safe or working system. The battery has to be correctly matched to the inverter. The wiring has to carry the current. The fuse has to protect the wiring and equipment. The disconnect has to give you a way to shut the battery off. The BMS has to monitor the cells and protect the battery. All of these parts have to work together. Now, let's talk about the 3 numbers that cause the most confusion: voltage, amp hours, and watt hours. Voltage tells us the electrical level of the battery system. A 12-volt system operates at a lower voltage than a 48-volt system. Amp hours tell us the charge capacity of the battery, but amp hours by themselves do not tell us the total amount of energy stored. To find the stored energy, we need both voltage and amp hours. The formula is simple. Volts multiplied by amp hours equals watt hours. Let's look at a 12.8-volt, 100 amp-hour battery. That battery stores about 1,280 watt-hours. 1,000 watt-hours equals 1 kilowatt-hour. So 1,280 watt-hours is 1.28 kilowatt-hours. Now let's look at a 25.6-volt, 100 amp-hour battery. That battery stores 2.56 kilowatt-hours. Now take a 51.2-volt, 100 amp-hour battery. That battery stores 5.12 kilowatt-hours. All three batteries are rated at 100 amp-hours, but they do not store the same amount of energy. The 48-volt battery stores 4 times as much energy as the 12-volt battery. This is why comparing batteries by amp-hours alone can be misleading. A 12-volt, 200 amp-hour battery and a 24-volt, 100 amp-hour battery store about the same amount of energy. The labels look different, but the total watt-hours are close to the same. This is also why kilowatt-hours are usually the better number to use when comparing batteries of different voltages. Now let's take that stored energy and connect it to something practical. Suppose we have a 51.2-volt, 100 amp-hour battery. We already know that it stores about 5,120 watt-hours. Now suppose we connect a load that uses 500 watts. On paper, that battery could run the 500-watt load for a little over 10 hours. But that is only the theoretical answer. In the real world, the runtime will usually be shorter. The inverter uses some power, the cables have some loss, the battery may have reserve settings, the load may turn on and off, or change its power draw. So the math gives us a starting point, not a guarantee. Now let's clear up another common mistake. Amp hours are not the same thing as amps. Amps tell us how much current is flowing right now. Amp hours tell us the capacity of the battery over time. A 100 amp-hour battery does not automatically push out 100 amps. The load determines how much current it pulls. A small light may pull very little current. A large inverter running an air conditioner may pull a great deal of current. The battery has to be able to supply that current safely. That brings us to the last part of this lesson: series and parallel connections. When batteries are connected in series, the voltage increases. Two 12.8-volt, 100 amp-hour batteries in series become a 25.6-volt, 100 amp-hour battery bank. The voltage doubles. The amp-hours stay the same. A simple way to remember it is, series adds voltage. When batteries are connected in parallel, the voltage stays the same, but the amp-hours increase. Two 12.8-volt, 100 amp-hour batteries in parallel become a 12.8-volt, 200 amp-hour battery bank. The voltage stays the same. The amp-hours double. The easy way to remember that is, parallel adds capacity. With 4 batteries, we can also build a series parallel bank. 2 batteries are connected in series to make one 25.6-volt, 100 amp-hour string. A second matching string is built the same way. Those 2 strings are then connected in parallel. The finished bank becomes 25.6 volts and 200 amp-hours. That bank stores about 5.12 kilowatt-hours. Here is the part that is easy to miss. The way the batteries are connected changes the voltage and amp-hour rating, but it does not create more energy. 4 12.8-volt, 100 amp-hour batteries contain about 5.12 kilowatt-hours total. They could be arranged as 12.8 volts at 400 amp-hours. They could be arranged as 25.6 volts at 200 amp-hours. Or they could be arranged as 51.2 volts at 100 amp-hours. The total energy is still about the same. We are only changing how that energy is delivered. Before connecting batteries together, they should normally match. That means the same chemistry, voltage, capacity, age, condition, and state of charge. Mixing batteries without understanding what you are doing can cause poor current sharing, imbalance, overheating, or damage. Always check the battery manufacturer's instructions before connecting batteries in series or parallel. This week is about understanding the words and the basic math. It is not an instruction to start connecting loose cells or large batteries together. Even a small LiFePO4 battery can supply enough current to melt tools, damage equipment, or cause a fire. Large battery banks increase that risk. Learn the system first, understand the connections, plan the protection, then build. The main points from this week are simple. A cell is the building block. A battery is made from cells. A battery bank is one or more batteries connected together. Volts multiplied by amp hours equals watt hours. Series increases voltage. Parallel increases amp hours. And voltage and amp hours together tell us how much energy is stored. Next week, we will take the next step and look at how to choose between a 12-volt, 24-volt, and 48-volt battery system. Please like and share the video so we can help more people understand how these systems really work.